Okay, in the last two classes, we saw basics of three-phase AC circuits, and we saw the difference between star connected and delta connected sources and star connected and delta connected load. So in today's class, we are going to discuss more about the power factor and the measurement of power in three-phase AC circuits. Okay, so in star connected three-phase circuits, we know the line voltages are given by √3 times the phase voltage, whereas the line current and the phase current are is same. Okay, so this is the thing which we need to remember. For an star connected source, the line voltage is √3 times the phase voltage, and the line current and the phase current are equal. Now if you try to find out what is the power, okay, that will be this is the source. Like, so there are three arms of the star connected source. So in each arm, the power will be the phase voltage into the phase current and the COSPHI. COSPHI is the angle phi is the angle between the phase current and the phase current and the phase voltage, right? So, and why are we multiplying it by 3? Because there are three such arms. Okay, now we are talking about a balanced system where the loads are balanced and the source is also balanced. That means all the three voltages are exactly the same, except that they are differing in phase by 120 degree. Okay, so the total power will be 3 into V phase into I phase into COSPHI. So this is one formula which we need to remember. Okay, for all computation and numerical examples. So this is the formula which we are going to use. So here we are talking in terms of phase voltage and the phase current. Now if you want to talk in terms of, if you want to compute power in terms of line voltage and line current, then okay, this line current is same as phase current for a star, so that will remain as it is, whereas the phase voltage, okay, is to be we know that the phase voltage is VL divided by √3, right? So if we going to substitute V phase here, okay, V phase here, right, with VL by √3. So VL by √3. So this 3 is already there. So 1 √3 is in the denominator. So they get cancelled, and I get √3 times VL IL into COSPHI. So these are the two formulas which we need to remember. If I am talking in terms of phase, it is just V phase into I phase into 3, because there are three arms into COSPHI. But if I am talking about the in terms of line voltages, and then it is √3 times line voltage into line current. Okay, for a star, again remember, for a star connected, I phase and IL are the same. Okay, so this is about star connection. Okay, whereas in delta connection, okay, if we see again the power in each of this arm will be 3 into V phase into I phase into COSPHI. So this formula essentially remains the same for both, right? V phase into I phase into COSPHI, because there are three arms. We are talking about the phase voltage into phase current. Okay, so that will be the power in each phase. So there are three phases, so it will come 3 into V phase into I phase into COSPHI. Now if you want to express the same thing in terms of line voltage, then now in this case we know for a delta connection that the line voltage and the phase voltage are the same, whereas the phase current is line voltage divided by √3. Okay, so this is for a delta connection, the line voltage is not same as that of phase, whereas the line voltage is same as the phase voltage, whereas the line current becomes √3 times phase voltage. So if I am going to substitute that out here, okay, if then VL by √3, so that √3 and this √3 gets cancelled. So again I get √3 times VL IL COSPHI. So if you see these two formulas and these two formulas, irrespective of star or delta, these two formulas remain the same. Okay, if I am talking in terms of phase voltages, then it is just 3 into phase voltage into phase current into COSPHI, or if I am talking in terms of line voltages and line currents, then there is an instead of 3 it is root 3 here, and line voltage into line current into COSPHI. So the formula essentially doesn't change here when we are going from star to delta. Okay, these two formulas are universal for both type of connections. Now if you take an example, things will be even more clear. Okay, so now it says a 3-phase 400 volt 50 hertz balanced supply. So when we when the question says like this, do remember this is the line voltage and not the phase voltage. Okay, if it is a phase voltage, it will be specified as a phase voltage, or it will be written, okay, 3 voltages are connected in this sequence and each voltage is 100 volts. Okay, terms to that, it will clearly indicate its phase. Okay, as long as it is just written that 400 volt 50 hertz, it means it is the line voltage. Okay, so it is 450 balance supply. It feeds a balanced load consisting of okay, it is we'll assume it is an star here star connected. It should have been specified. Okay, nevertheless, consisting of an 3-phase 3 equal single phase loads connected in a star, and a 3-phase heating load purely resistive. Okay, so the load is actually it's a star connected loads, but there are two kinds of loads which are connected. One is 40 plus J30, and the other one is again a star connected 3-phase heating load whose resistance value is not given, but the power is given here. Right, so this is a representation of only single phase. Okay, there are 3 phases, but only single phase is shown here. So you have an phase voltage out here. Okay, and then you have these loads which are connected. So we are trying to analyze what is happening in single phase, and then we will extrapolate it for the 3-phase supply. Okay, so if you see here, so this is ZL is 40 plus J30, which is given here. So phase voltage is going to be line voltage divided by root 3. Okay, this is the phase voltage which is given here. So 400 volt divided by root 3, this is 230.9. Okay, 400 volt is the one which we get in our houses. We generally call it as 230, but if you compute it correctly, it will come to 230.9. Okay, it is in fact the other way around. It is 230 is the one which comes in our home, and this will be slightly more than 400. Okay, so this is the phase voltage. Now if I have to find out the phase, this is one. Okay, Z. So what about the other one? So I can compute the current also. So IP is 230 divided by 40 plus J30. So I can compute the current also. Now there is one more element which is connected, whose resistance value is not given, but the power is given. Okay, now power is given as 1.8 kilowatt. Okay, now remember this is an 1.8 kilowatt is not for a single arm of the load, but it is for the entire 3-phase load. Okay, but here we are trying to find out the current in a phase. So we need to divide this 1.8 divided by 3, so 600 watts. So 600 watts is per phase. Okay, so the total 600 plus 600 plus 600 is 1.k kVA. That is for the 3-phase. For a single phase equivalent, I have to divide it by 3, and I get 600 watts here. Right, so now again 600 watts divided by the phase voltage, I'll get the phase current. Now I can add these two. There are two loads now which are connected in parallel, so I can add those two currents, and I can get the total phase current out here. Okay, and now that becomes the supply current. What is supply current? It is the line current. Okay, line current sometimes is known as supply current. So in a star network, we know the line voltage is the line current is equal to the phase current, and that's why the phase current is the same. Okay, whatever line current, phase current we got. Phase current is sum of the two currents in the two loads which are going, and now the total line current is going to be the sum of these two. Okay, so this is known as the supply current or line current, or it is same as the phase current. Okay, now power supply factor. Okay, now where did we get this cos minus 23 here? If I go back here, when I try to find out what is the phase current, okay, this when I divide this voltage divided by this vector, which is the impedance which is given here, so I get minus 37.7, and then I have to add that with the resistive load, right? There is one more resistive load, so I get an vector here. So this 23.7 is the phase. Since it is negative, it means it is lagging. So if I have to tell, so I take a cos of 23.77, which is 0.915, and I say it is lag out here. Okay, either I can say the phase power factor is minus 23.77 minus 0.915, or I can call it 0.915 lagging. Okay, so that is the power factor. Okay, so once you get the power, now active power supplied. Okay, now we know we can use either of these formulas, 3 times V phase into I phase, or root 3 times VL into IL cos phi. So there are two formulas, right? Either of them we can use that to compute the power. Okay, now if I do root 3 VL into instead of cos phi, if I put sin phi, then I get the reactive power. Okay, is it understood how to do these problems, Gagan? Pranav?
Yes, sir.
Yeah, Pranava, is it okay? Yeah. Okay. So they could be now we were talking about an balanced load, but not necessarily the loads will be balanced always. Okay, there will be situations when the loads are not balanced. Okay, this will generally happen. So suppose you have a 3-phase power supply coming to your house. Some rooms will be connected with one phase, some other rooms will be connected with some other phase. Maybe your fridge will be connected to one phase, and a room heater to some other phase. So all of them don't work at the same time, and they don't draw the same current. So in practical situations, the loads need not be the same. Okay, in that case, how to find out what is the current? Again, it is simple. For a star connected, we know what is the phase voltage. You have to divide the phase voltages by the impedance which is there in that phase to get the phase currents. Okay, so IA, so in this one is 15, so I divide by 15. The next phase here is 100, because it is given a balanced phase voltage. So in this problem, see, it is clearly defined. It is a phase voltage of 100 volt. Okay, so it is phase voltage, so 120 and minus 120. So we need to be careful with these angles, okay, when we are finding out the values of the currents. Otherwise the net power factor and things, and they will get you will get an erroneous answer if you don't take care of these angle aspects. Okay, so this is 120, and this is minus 120, or you can write 240, whichever is comfortable. So you divide by the individual whatever is the individual loads which are connected in each of these phases. So you get 3 different phase currents with different phase, and if you see, these are not differing each other by 120 now. Okay, the magnitude is different, and the phase voltage, they are not in case of a balanced load, all these magnitudes will be same, and they will differ from each other in phase by 120 degree. So since it's an unbalanced system, you will find the magnitudes are different, and also the angles are different. And we also saw that in a balanced system there is no neutral current, but however in an imbalanced system or an unbalanced system, there will be a net neutral current flowing. Okay, so these 3 currents will not cancel each other. So if you take the algebraic sum of all these 3, so you will get a net neutral current. Okay, so so there will be a neutral current also which will be flowing. Okay, so this situation should be avoided as far as possible. Okay, so that is why it is so whenever there is an so that is generally taken care of by the electricity department for distribution of supply to the various colonies. And within the house, when you are doing connections also, you should be careful that maximum that the load is evenly distributed. Okay, so this is not a very ideal condition. So now how to measure the power? Okay, so there are three ways of measuring the power. There is one is known as the 3-Wattmeter method. This is the simplest and straightforward method. So in each of these phase you connect one wattmeter. So this will whether it is balanced or it is not balanced. Okay, so it doesn't really matter. It will give you the result. Okay, you just have to add the power which is recorded by all the 3 wattmeters. Okay. Again you have an 2-Wattmeter method. Here also you can use this 2-Wattmeter method for balanced as well as unbalanced or star or delta. Okay, this is a 3-Wattmeter method. It has to be star. Okay, we'll see why star is required. Whereas 2-Wattmeter method, it can be star or delta, doesn't matter. Okay, and it could and it can be balanced or unbalanced, again it doesn't matter, but for power factor it has to be balanced. We'll see those details slowly. Okay, in 1-Wattmeter method, a single wattmeter is required. Again it cannot be delta, it has to be star connected, and it has to be a balanced load. Okay, so since the power is 3 times, if it is a balance, so you just compute the power in one phase and multiply it by 3. So that is 1-Wattmeter method. Okay, how do we measure is what is a wattmeter? Wattmeter multiplies the voltage and the current, and then and also it takes care into the cos of angle between the voltage and the current. So you need to feed the current and voltage into the wattmeter, right? So have you done instrumentation course as of now? Have you learnt about wattmeters? No?
Voltmeters?
Wattmeters.
Sir, what's that?
Wattmeter.
Yeah,
Yeah, you have done it in your basic classes. Okay, so for a wattmeter you need to feed the current as well as the voltage. So current means you connect, and so the terminals, there will be a coil which is connected in series. So this coil will sense the current which is flowing. So it's a series coil which offers negligible resistance, and also there will be a coil which will sense the voltage, but this voltage sensing coil is generally connected with a large resistance in series. So that is why the number of coils it's shown here high. Resistance in series, or very high inductance coil it is, because the purpose is only to sense the voltage, and there ideally no current should flow in this. Okay, so this is a resistance which is connected in series out here. Okay, this is not the load here, this is the star load. This is the resistance which is connected in series with the voltage coil of the wattmeter. So this is how a wattmeter is connected. Okay, this is for an 2-Wattmeter. This is for a single wattmeter method. We can do this. Okay, so we are going to no, this is just an diagram which is showing how a wattmeter is connected. So this is 2-Wattmeter method. Okay, so if you see here, this is wattmeter 1, in which you are connecting the current coil in series with the line out here, and the voltage coil between R and Y. So this is how we are connecting here. Similarly, you have a second wattmeter between B and Y. Okay, so if you see, so there are 2 wattmeters here. Okay, so one line is taken as common out here, and there are 2 wattmeters which are taken. So this is going to measure the voltage between this and this, and the current here. The second wattmeter is going to take the voltage between this and this, and the current which is now flowing here. Okay, once you connect that, okay, now once you have connected it here like this, right? So what is the total power of the system? It is like an Rn, I, which is current which is flowing, and Rn. This is the VR. This is R, B, and Y stands for red, blue, and yellow. Okay, there are the 3 colors. Okay, so that what is the total power will be Rn, Vrn into IRn, right? Or I just call IR, right? Plus IY, that is the current which is flowing here, into the voltage, that is Vyn, and plus this this power out here, which is IB. okay, IB into VBN. Okay, so these are the, if you add these three, then you get the total power, right? Now what is the power which is being sensed by this wattmeter? Okay, IR. So the current flowing, it is sensing this current, so I write IR. And what is the voltage it is sensing? It is taking the difference of the voltage between VR and R and Vy, right? So I write, so the voltage is Vrn minus Vyn. Okay, is this understood, Gagan? Where did this equation come from? P1 is equal to IR in bracket Vrn minus Vy.
Yes, sir.
Okay. Similarly, if I have to find out what is the power which is being measured by this wattmeter, so this is the current which is flowing here. So IB into what is the voltage? Voltage is VBN minus, okay, this line voltage, this voltage is VBN, right? B with respect to N. And what is this voltage? This is VYN. So I write VBN minus VIN, right? So now I have, what is the total voltage P1 plus P2 if I write, so I can add these two equations out here, right? So I write this, there is a minus here, there is a minus here, and it is VYN. So I take that common, so IR plus IB. Okay, now we also know that from this node equation, if I write this node equation, IR plus IY plus IB is equal to 0, because all the currents are converging at here. So the net current has to be 0, the algebraic sum of these three currents. So I write these equations, or minus IR plus IB I can write as minus IY. So if I substitute here, okay, IR plus IB as minus IY, so that minus and this minus becomes plus, IY plus IB. So this is the P1 plus P2 becomes IR VRN plus IB VBN plus IY VBN. Okay, and what is this? This we initially discussed, this is the total power. So in a 2-wattmeter method, when I connect 2 wattmeters like this, the sum of these 2 wattmeter readings will give the total power. Okay, so you don't require actually 3 wattmeters out here. It is a star connected load, or it could be delta connected load also. It is not going to make any difference whatever way the configuration is. You have to connect this between these three lines. This is the way you connect 2 wattmeters, and you just add these two voltages to get the total power. Okay, so P1 plus P2 will give the total power. Okay, now also if it is in this case the loads need not be balanced also. Even if it is unbalanced, still P1 plus P2 will give the total power. Okay, but we cannot tell the total power factor. Okay, because power factor doesn't make any sense here, because in an unbalanced load, the power factor doesn't make any sense, because power factor will be different for each of these three arms, right? So you cannot say what is the total power factor. Okay, it will be different if it is unbalanced load. For a balanced load, power factor makes sense. Okay, so for a balanced load, by connecting these two powers and you add these two powers, you will get the total power. But what is the power factor? If you want to find out what is the power factor, and if you get the power factor, then you can also tell what is the reactive power also in that case, right? So here for a balanced load, I can find out using the power factor method, 2-wattmeter method. I can even compute the power factor. Okay, if it is unbalanced load, then the power factor, you can just find out what is the total power. If it is a balanced load with 2-wattmeter, I can, apart from finding out the total power, I can also compute the power factor. So how do I compute the power factor? Okay, if you see, these are the 2 wattmeters which are connected here, right? What is P1? P1 is VRB into IR into COSPHI. Okay, now COSPHI is the, if there is a difference between what the COSPHI is, the phase angle difference between the current and that particular phase, right? So you get one equation out here. Now if you see here, what is VRB? VRB is VR minus VB. Okay, minus VB is this. Okay, which is VBN is here. Okay, now minus VB you take an negative of that, and then you do the vector sum of that. Okay, it is like converting the line voltages into phase voltages. So you get root 3 VN IR cos 30 plus 5. Okay, this is simply the from the line voltage you are writing the now here you are representing the phase voltage out here. Okay, so you get this equation. Similarly, if you do this for P2, I can write again. I can if I write in terms of the line voltage, okay, I can write root 3 VN VL cos 30 plus 5. Okay, sorry, this will be minus 5 out here. Okay, if you do the computation, you will see it is minus 5. It is coming out to be minus 5 in this case. So you have these two equations. Okay, so P1 will be the cos 30 plus 5 and 30 minus 5. So if you divide these two, because the line, it is a balanced load, so that's why I said it is applicable only to a balanced load. So this IR, IL and VR and VL, these will be equal. Okay, IR will be equal to IL and IRN will be equal to VYN. Okay, this will be IY again. Okay, so sorry, so there is a mistake there. Let me correct it straight away. So this is I Y, okay, and this is again I Y. Okay. So if you okay, another thing was this would be negative out here. Okay. So if you divide these two things, you will get a P1 by P2 as cos 30 minus 5 and cos 30 plus 5, and then by applying compendo and dividendo, you get this equation where it's tan phi is equal to root 3 P1 minus P2 and P1 plus P2. Okay, so if I have to summarize it, if I put 2 wattmeters in a balanced load, then I can find out the total power will be given by P1 plus P2, and if I have to compute the power factor, then I can use this formula. Okay, where this is the phase angle between the so cos phi will give the power factor. For tan phi you use this formula. Okay, root 3 into P1 minus P2 and P1 plus P2. Okay. So here some things we need to remember here. Now if there is no power, if it is a pure resistive load and there is no difference between the here, if it is no difference between the phase and the line currents, then you will get this as 0 and you will get P1 is equal to P2. Okay, but in case there is an reactive element, then you will find there could be two possibilities. One is phase is equal, if it is less than 0, then both P1 and P2 will be positive and you can get the total power P1 plus P2. Okay, and there could be a possibility that the phase is greater than 60. Okay, in that case, okay, it will be negative, P2 will be negative, right? But these wattmeters, if I go back here, these wattmeters, if it's an analog wattmeter, it may not be able to read negative values because it will start from 0 only. So in that case, the current direction terminals, they need to be changed to get the readings. If you have to read, if it is showing 0 in spite of some load being connected, that means the phase angle is greater than 60, and that is why it is not able to register the negative value. So you need to interchange the connections out here. Okay, so and then read and then assume and then if it is reading say 60 watts, you have to take it as minus 60 watts. Okay, so if the wattmeter can read negative as well as positive values, then you don't have to do anything, but that is not the case generally. It will read only all the analog analog wattmeters especially, and they'll read only the positive values. So in case it is showing 0, you might have to swap the connections, these terminal connections, and then it will read some value, and since you have swapped the terminals, the net reading you need to take it as negative. Okay. So that will be clear in this example. So in a 2-wattmeter method was used to determine the input power to a 3-phase meter. The readings are 5.2 kilowatt and minus 1.7 kilowatt. Okay. So how did this you get minus 1.7? Initially, say somebody connected it in the correct sequence. It was reading 0. Because it was not registering negative, so he swapped that terminals. So once swapping the terminals, he would read 1.7, but since he has swapped it, he will note it down as minus 1.7 kilowatt. Okay, so that is how we get minus, and the line voltage is given as 415 volt. Calculate the total power factor and the line current. Okay. Total power is adding these two, so 5.2 and it is minus 1.7, so I write minus 1.7, so 3.5 is the total power, right? And to calculate the power factor, tan phi, I use this formula, root 3 into P1 minus P2. So 5.2 minus 1.7 it is, so I get 3.41, and then for phi I take tan inverse of that, you get the angles in degrees, and then for power factor you take cos phi, so you will get this is the power factor. Okay. And now I need to find out what is the current. Okay, now this is the total power 3.5, phase power factor is known, and the line current, I have to find out the line current, so I am using the formula root 3 into line voltage into line current, and line voltage is given in the problem as 415 volt. So this is 415, so 415 volt I am putting it there, so I get the line voltage here using this formula. Okay, so this is that power is equal to root 3 into line voltage into line current into power factor. Okay, I am using that formula to obtain the line voltage. Right now, 3-wattmeter method, like I said, it is fairly simple. It can be used only for an 4-wire system, where I connect 3 separate wattmeters between each of the phase and the neutral. Okay, so it will just be sum of these 3. The total power will be sum of these 3 voltages. Okay, so this is the simplest one, but it is only applicable for 4-wire system. It cannot be used for an 3-wire system. So 3-wattmeter system. So there is a problem given out here. It says there are 3 W1, W2, W3 connected to 3-phase ABC. The balance source is Y connected, and phase voltage is 100 volt in AB. Find the wattmeter reading. So these things are given here, right? The impedances are given here, and in this system also again these need not be balanced. Okay, even if it is unbalanced, still because individually you are measuring the power in each of these 3 arms with respect to the neutral voltage. So even if it is imbalanced, there will be no error if you are computing the power and doing a sum of these 3 powers. Okay, so 15, each, now this voltage is known, right? So this 100 volt is again given phase voltage. Okay, remember, this is not the line voltage, it is specified, it is as 100 volt. Okay, so 100 divided by 15, 100 divided by 10 plus 5j, and 100 divided by 6 minus aj, so that will give the 3 currents. So you find out these 3 currents out here. Okay, and then powers in each of these 3. Okay, that is voltage into current into we have to take the real value of that to find out what is the power, right? The true power. So that is why these voltage and to currents, these voltages in these cases, all the 1, 2, 3 volt currents are given, and you multiply it with the voltage, and then you take the real part of that. Okay, so you get the 3 powers, and the total power will be sum of these 3 powers. So this is the simplest way. Okay, you can also do this I square R, you will get the same value. You can do that also, I square into the I square, magnitude of I square, if you see, and only the magnitudes can be done I square R for, and then you can add it up. So you can do this or this. Okay, this is known as 3-Wattmeter method. Okay, so that's all. So for today, in Monday's class, we'll see some numericals on 3-phase power supply. Okay, thanks a lot.
Thank you, sir.